Okay, hey guys, so in this video I'll show you how to make a simple digit recognition script. So if you go to my GitHub, we'll be making this piece of code here, and it's just a super simple script. It imports a few things. We're not actually going to use Torch features, we're just going to use the tensors. So that's the only reason I've imported Torch, but all the code is like really low level and it's good for understanding how this stuff works. So this is for inputting, for reading the CSV file, and then this is the actual neural network code. It's not even that long, and then here we just plot the loss, and here you can see each iteration gets a lower loss, and the final accuracy is 83%. I have gotten the accuracy up to like high 90s if you just keep running this for like an hour. I'm running it on like the CPU of my MacBook Air, so that's the only reason it's 83% here, because this ran for a few seconds. So yeah, so let's get into it. So I'll just create a new Jupyter notebook, and I'll just start by pasting in code and then I'll discuss what it does. So first we'll paste in this. You probably know what Torch is. We also import NumPy for math, and then this is for plotting data, and Pandas is for reading in the CSV like really efficiently. So the next piece of code here, this just reads the CSV and turns it into a list, and then I print out that we've read the images, and then we type out how many images there is in the test CSV file. So there's around like 50,000, I think. I'm not quite sure, but yeah. And then we turn it into a NumPy array, and then the number of samples is just the amount of images there is in the training samples. And then here, this piece of code is just because we want to have a validation set of like 1,000 at the end. So we keep all of the images for training, and then we keep like 1,000 at the end for validation when we're tuning hyperparameters. So this next little piece of code, this is our training and this is our testing that we're going to be using. So I'm not going to go into the details, but this pretty much just turns it into a one-dimensional array that's 0 to 1. So we take the values that are 0 to 255 and crush it down to 0 to 1, and these are going to be the floats that we input into the array. So there's like 784 or 28 squared, yeah, 784 floats that we input into the first layer, which is the input layer, and this is like the same thing here. It's just our data. So if we run this and then run this, it'll take a second here, but we should see that it outputs the number of test images. Okay, so here's the first problem. Okay, make sure you have a CSV file with this exact name. You can find it in my GitHub, or you can find it in like on the internet, download a CSV file. But I already have it here, so I'll just go ahead and save this tutorial. And now if we run it, it should be fine. Okay, yeah, so we've got 50,000 images in the data set. The last 1,000 we use for validation. And now we get into the actual fun stuff. So I'll just put in a block of code. It's going to look a bit scary, but I'll discuss it. So this is the hidden layer size. This is the amount of neurons in the hidden layer. And for this network, we're going to have an input layer and a hidden layer, and then the output layer, I'm pretty sure. Oh, no, we have two hidden layers. So we have two hidden layers of size 100. So we'll have 700, I'll just put a comment here, 784 for input, and then 100 hidden, and then 100 hidden, and then 10 for output. So the first weights, this is for the first hidden layer here, this part. Oh, sorry, it's like this. So the first weight is from this layer to this layer, from the input to the first hidden layer, And then the second weights is from the hidden layer to the output layer. And then same with the biases is for these connections here. And we changed the X train and Y train to a NumPy tensor instead of or a torch tensor instead of a NumPy you'll see in a bit. And now we just define a few functions. So we define the ReLU. ReLU just looks like, you probably know what ReLU looks like, but it's just this. So if it's below 0, it returns 0. If it's above 0, it just returns the number. Then for softmax, you've also probably seen what softmax is. It just turns the inputs into probabilities. So instead of having like output neurons like random numbers, it gives us probabilities that sum up to 1. And then here we have ReLU derivative. So the ReLU derivative is literally just, if it's above 0, return 1. If it's below 0, return 0. Softmax derivative is a bit more complicated, but you can just find it by searching it up and typing it in like this. Alright, so now moving on to a few more hyperparameters that we have here. So we set the learning rate. This you can move up and down. I found that 0.3 works well for the training I did, which is like 2 seconds of training. So you might want to lower it to like that or something when you actually run it for longer periods of time. We've got the mini batch size and we've got the amount of iterations before it stops. Now I'm going to paste in the rest of this and just discuss what it does. Okay, so this is where we ended. Okay, so this is just a list where we're going to store the loss to be able to plot it later. So this is not really important. But here for each iteration, first we get the mini batch. So we get random training data from the set, and we get random training data so that it's different each time, and we can get slightly different learning each time instead of getting like the first 100, next 100, and so on. So, and then we get the indices, and then this just creates like, instead of X-train, we use the X-train mini batch. Alright, so then for the forward pass, this is pretty much the equivalent of thinking of like a linear layer. The tensors, it's like a dot product or something like that. I'm not like 100% sure. But this is the equivalent of like a linear layer, and then we add the bias, and then we apply the ReLU function. And we do this for both layers. Now once we've done the forward pass, we calculate the negative log loss, and this just tells us how far off the neural network is from what we want it to output. Because we have the output, the Y training mini batch, and we just compare it and see how well it's done. And now for the backward pass, we work our way through. This is just manual backpropagation. Most people would use like lost out backwards on Torch. I won't really go into this because this would take like a long time to explain, but you just work your way back, calculating the derivatives for the biases and the weights, and then here we simply update the weights. So weight 1 equals the weight minus the learning rate times the weight, and you can actually write minus equals on here, and it should do the same thing. Minus equals. So we just subtract learning rate times bias, and the reason we subtract is because we don't want to go up the incline, we want to go down the incline. If you imagine it like so if you imagine it like a ball rolling down a hill, like a lot of people use this example, when you do backpropagation, you get the derivative, and the positive way makes you go up, but we want to minimize it. So you apply the negative of the derivative, like subtract the derivative, and you'll move your way down until you get to a local minimum, and you get the lowest loss there, which means you get the best predictions in your neural network. Then here we just append the loss, and every 100 iterations we'll print the iteration and we'll print the log loss. And that's all we got to do for now. So let's just run this and as you can see, we get this. And now this next piece of code, we test it on 1,000 test images. So we pretty much just start with counting the correct amount. So we set it to 0, and since we know we're doing 1,000, we just divide by 10 after to get the percentage. Like if you think about it, you'll divide by 1,000 and then multiply by 100 to get the percent. It's the same as just dividing by 10. So then for the range from 0 to 1,000, we forward the first layer. So this is the exact same thing we saw above, like linear layer, a ReLU, and then another linear layer, and then at the end, this literally just checks, is the highest number that we outputted the same as the highest number outputted here. So as we said earlier, here the output is 10. So if the first number is the highest, that means it thinks it's a 0. If the second number is highest, it thinks it's a 1, and so on. So here, it looks at the highest number. That's what argmax does. And it checks if, for example, our highest value was in the 5th slot, and it compares it to if the highest value here is in the 5th slot. And if it is, then we increase correct by 1. We increment it by 1. So that just checks if what we outputted is the same as what we expect it to output, if that makes sense. Alright, so now we'll move on to plotting the loss. This is just a simple little piece of code. It plots the loss, and as you can see, it goes down. The reason, so one important thing to note, I'll just go over a few notes. We multiply this by 0.1 because if you look at this, if we run it, sorry, I have to run this to reset the stuff, then run this. Okay, the accuracy is garbage, something is broken. But yeah, you can see you gotta multiply it by 0.1. We'll see if it works now. Yeah, so we got accuracy of 84%. But the reason you gotta multiply it by 0.01 is because it will guess at the start, it'll use random weights, and it'll guess wrongly. Like our loss would be so bad that it doesn't actually learn. So I'll try to get this to work like badly with a bad example. We'll set the iterations to something like 3200. We'll run this, because I want to show you, it gives like a hockey stick shape, and it's because it's guessing wrongly. And yeah, you can see it starts off really high and wrong, and then it quickly works its way down. So by multiplying by 0.01 or lower, you can skip this whole section here, and it just means you skip some iterations and save some computing power. A few other things to note that I'll just go over. The backwards pass, many people just use the, I'll show you another script here. This uses the torch backward pass. So with this, you can get a much higher accuracy. I was able to get 97.99 with this, or 98. This just trained for a lot longer time, as well as implementing some dropout and some other things. You can look at this in the GitHub as well. But I think the best way for you to learn about these neural networks is by going through the code, changing up parameters, and trying to understand like what does this part do, what does this part do, and so on, and like mess around with the code. Someone that I would highly recommend watching is Andrej Karpathy on YouTube. He makes some really good videos on this kind of stuff. He hasn't made the digit recognition stuff, but he's made some other good videos on like backpropagation and like next character prediction models and so on. So he goes into more depth about the actual backpropagation, but hopefully this is a good introduction on like the basics of how people get these things to work, and just some simple code for you to look at. I will be making some more theory related videos on this topic, like going over the terms like regularization techniques, like dropout, early stopping, and so on with like some actual graphs, as well as like data augmentation and stuff. So make sure to subscribe to check that out, and yeah, see you later.